All that remains is to specify the set of possible impurity criteria. As already seen, the variance is a measure of impurity when the output is continuous. The variance is the most common criterion in regression. Another criterion implemented in Python is the mean absolute deviation around the median, defined by the formula 4, where the term med yi xi in A corresponds to the median of yi of the observation belonging to the cell A. In the framework of the K-class classification, K can be greater than or equal to 2, 3 impurities can come into play. To define them, let us note pKn of A, the proportion of observations of class K within the cell A. The first impurity is the error rate, which is defined as 1 minus the maximum over K of pKn of A. This quantity corresponds to the probability of being incorrect when predicting with the majority class in the cell A. It is thus a quite natural measure of the impurity of a cell. The next two measures are a bit more complex, the Gini criterion and the entropy. The Gini criterion, defined in 4, can be interpreted as the error of a classifier predicting the class K with probability pKn of A in any cell A. The entropy, on the other hand, is a measure commonly used in different domains, notably physics and computer science, to measure the dispersion of a quantity. Each splitting criterion can lead to different trees with different performances. Among the existing criteria, the variance is the most used in regression, and Gini and entropy are used in classification. In particular, the error rate is never used as a splitting criterion. Let us now see a link between the chosen splitting criterion and the risk, which allows us to measure the overall quality of our estimator. To understand this link, let us consider the impurity based on the variance, whose formula is recalled here for any cell A. For any split represented by a direction J and a position S within cell A, the splitting criterion, i.e. the variance reduction, evaluated in this split, is defined as follows and can be rewritten as 7, where y bar AL, respectively y bar AR, is the mean of yi in cell AL, respectively in cell AR. Note that the first term of equation 7 does not depend on the considered split, i.e. on the couple JS. Therefore, maximizing the splitting criterion is equivalent to minimizing the second term, i.e. this expression. This quantity is simply interpreted as an average computed on all the observations of the considered cell A. Note that for each observation I, the term subtracted from yi is y bar AL if point xi belongs to cell AL, and y bar AR if point xi belongs to cell AR. The term inside the square is therefore the difference between yi, the true label of the point, and a prediction equal to the average of the labels yi's in the left or right cell, depending on whether the point xi belongs to the left or right cell. In other words, the complete expression corresponds to the quadratic risk computed on the training set of the piecewise constant estimator in the left and right cell that outputs the means in the left and right cells. Finding the split that minimizes this quantity is the same as finding the split that minimizes the quadratic risk of this piecewise constant estimator, corresponding to the estimate produced by the tree if the construction was stopped at this stage. So you can see that the impurity related to the variance is naturally associated with the quadratic risk. Our goal in statistics is to build the estimator with the lowest risk. We would therefore like to find the optimal tree, i.e. the one with the lowest squared error. However, this problem is extremely complex to solve because it requires to jointly optimize all the splits in the tree. For a dataset containing n observations, there are n-1 splits to jointly optimize, which is often unfeasible for classical datasets. A classical technique to circumvent this computational problem is to consider a greedy algorithm. Such strategies consist in splitting the initial method into elementary tasks and optimizing the parameters of each elementary task sequentially. The result is then not optimal, but is often a good approximation. In all cases, the obtained method is usable in practice, contrary to the global optimization, which is often too expensive in terms of computation time. Regarding trees, instead of finding the optimal partition, which requires to optimize jointly all the split of the tree, we optimize each cut at each step sequentially. In particular, a cut is not chosen according to the quality of the following cuts that could be constructed. To come back to the link between the splitting criterion and the risk of the tree, each risk has an associated splitting criterion. In each cell, this criterion, evaluated at a split, is nothing but the risk of a piecewise constant estimator in each resulting cell that outputs the mean or the majority vote in each cell. Given a risk measure, for example the quadratic risk, a splitting criterion can naturally be chosen. Here, the criterion associated with the variance. Since the optimization of the criterion is local, there is no theoretical guarantee stating that it is better to use the splitting criterion associated with the risk considered. Nevertheless, this practice is a very reasonable choice. Several splitting criteria are possible, as we have seen. The variance criterion corresponds to the quadratic risk. The criterion of the mean absolute deviation around the median is close to the L1 risk. For classification, the impurity criterion associated with the entropy corresponds to the cross-entropy loss often used in machine learning. The Gini criterion does not correspond to any loss because it does not correspond to a constant prediction in a cell, but to a random prediction. The error rate corresponds to the 0,1 loss, which should not be used as a criterion for building the tree, as we will detail in the next video. In classification, 3 splitting criteria are available: the error rate, the Gini index, or the entropy. Let's take the case of a binary classification. The error rate is then written as 1 minus the maximum over k of pkn of A. This corresponds to the error resulting from a prediction by a majority vote. In binary classification, the Gini criterion is written as 2 times p0n times 1 minus p0n, where p0n is a proportion of points with label 0 in cell A. Note that the same formula is valid when replacing the proportion of 0 with the proportion of 1. Indeed, this formula is unchanged when replacing p with 1 minus p. Now let's look at a particular example. Imagine that in the root cell of a tree, we have 900 orange observations and 100 blue observations. A cut is used to divide these observations into 2 sets. 2 cells are thus created. The right cell contains 200 orange observations and no blue observations, and the left cell contains 700 orange observations and 100 blue observations. We can calculate the impurity reduction associated with such a split. If the error rate is chosen as the impurity measure, the impurity reduction is 0. Indeed, the error rate is the same in the root of the tree and in the 2 cells resulting from the split. As a decrease in impurity informs us about the relevance of the split, we deduce that the cut considered is not informative. However, if you look at the situation, you can see that we have obtained a cell, the one on the right, in which the prediction is perfect. This split, therefore, allows us to predict the output more accurately, so it is informative. Whatever impurity measure we consider, we would like it to allow us to conclude that this split is informative, which is not the case with the error rate. Both the Gini criterion and the entropy lead to a non-zero impurity reduction, which are respectively 0.005 and 0.01. Note that we will never compare the impurity reductions associated with 2 different measures. The fact that the impurity reduction with the entropy is greater than that with Gini is therefore not interesting. This example shows us that the error rate should not be used to build a tree, since it does not allow to account for the quality of a cut. The fact that the error rate is a bad indicator corresponds to the fact that the associated error function is not strictly concave, contrary to that associated to Gini and entropy. You can find more explanations by following the link below. In any case, you must remember that the error rate is not precise enough to account for the quality of a split and should therefore not be used to build a tree. Nevertheless, it is interesting because it will be used in the pruning stage that we will see later.